Hello, IB students. In this lecture, we're going to talk about Newton's three laws. So first of all is Newton's first law. So Newton's first law states that if an object experiences no external force, or if the net force on the object is zero, it will either remain constant or stay in a uniform motion. Right, so it goes in a straight line at a constant velocity, right? So if there is no external force acting on this object, its state of motion will not change. So its state of motion just means its velocity, right? Its velocity will not change. So it either remains constant or it goes out in a in a stationary velocity, in a constant velocity, it just goes forward, right? So keep in mind that the object cannot change its direction, because changing its direction is the change of velocity. Remember, in the velocity lecture, we've talked about that velocity is a vector. So a vector has a magnitude and direction, and changing the magnitude or the direction changes the velocity, right? So for example, I'm going north right now at 2 meters per second, and now I change my velocity to going east 2 meters per second. Although my speed, which is the magnitude of my velocity, does not change, my direction have changed, which means my state of motion have changed, which means there must be an external force which acts on me, right? And why is Newton's first law true? Well, that is gonna relate it to the fundamentality of force. Have you ever think about what exactly is force? It's an intuitive concept. We push things, we pull it to make things move. So what is force? It's intuitively understood as the quantity, or as the thing, the abstract things which cause something to move. And that will be correct. The actual definition of force in physics is that force is the cause of acceleration, right? Remember, what is acceleration? It is change of velocity in a given period of time. So force is the cause of the change of velocity, right? So this means if I don't cast a force on an object, its velocity will never change, right? Force is the cause of acceleration. When I cast a force on an object, that object experiences instantaneous acceleration. It started to instantaneously accelerate on the direction which I'm acting my force on that object, right? For example, when I jump off of a building, why do I fall? Because I experience the force from Earth's gravitational pull, right? So it is the gravitational force which I experienced, which gave rise to my acceleration straight downwards, which in time, AT is equal to delta V, which in time changes my velocity and makes me fall. My velocity is downward, makes me travel downward, which is intuitively understand it as falling, right? So this is the explanation of gravity, and we can also use this to explain circular motion. So Earth is orbiting the sun 1 year per 1 year per revolution. So the only reason why it is doing circular motion is because that it is externally experiencing a gravitational pull force from the sun, right? So which gave rise to a acceleration which is perpendicular to its direction of motion, and this acceleration causes the Earth to go in an orbit instead of traveling straight out in this direction into this deep space. And you might ask, well, why is the force or the acceleration need to be perpendicular? Well, we don't actually need to understand right now. However, that's just something you need to know. That's kind of a spoiler. All right, so this is Newton's first law. All right, so now let's take a look at Newton's third law. So Newton's third law states that if object A casts a force on object B, then object A must experience a force with the same magnitude and the opposite direction. So opposite direction just means 180-degree turn, right? So must experience a force with the same magnitude and opposite direction with object B. So this basically means that in real life, if I punch someone, well, my palms are gonna hurt too, right? Their face, surely it's gonna hurt, but my palm will experience the same force, right? So if I punch someone, my palm will cast a force on their face. However, their face will cast a force with the same magnitude and the opposite direction to my hand, and that is Newton's third law. So there are some strange scenarios or strange application of Newton's third law, which is, for example, if I am falling, on the earth, the reason why I'm falling is because I'm experiencing the gravitational pull from the earth, which changes my velocity, which gives me the acceleration as I'm going downwards, right? So I am experiencing a downward force from the earth due to gravity. So according to Newton's third law, the earth should experience the same force which I experience with the opposite direction, and this force, these two forces are considered as the opposite force. All right, so you need to distinguish between opposite force and equilibrium force. For example, if I am standing on the ground, well, I experience downward gravity and I experience the reaction force. All right, so normal reaction force. So normal reaction force just means the force which is keeping me not falling down, the force that the ground is pulling up on me. So right, so these two forces are considered as equilibrium force because they keeps me in stationary. According to Newton's first law, so I experience downward gravity. This means I should travel downward. This means I should have an acceleration downward, right? So the reason why I am not actually going through the earth is because the earth is giving me an upward force which is the same magnitude and opposite direction to my gravity, and these two forces combine together and I have a net force of zero. So when I have a net force of zero, there is no external force acting on me. I must stay stationary or travel in constant motion. So this is Newton's first law, remember that. So these two are considered as equilibrium force, which is the force which keeps me in constant, right? So the opposite force is that I am experiencing downward gravitational force from Earth, and the Earth is experiencing upward gravitational pull from me. So that is the opposite force, right? So this is something you need to distinguish. All right, so let's actually look at a work example. All right, so there is a plane. This is a plane. Don't question my drawing ability. All right. So this is a plane, right? So it experiences downward force, downward gravitational force, and the reason why it's floating in the air is because it experiences the lifting force from air, right? So this is the force, which is the air is lifting it, and I want you to figure out the force which is opposite to the lifting force. I want you to figure out the opposite force of the lifting force, all right? So pause the video and think about that right now. And the actual answer is that while the air molecule is giving a lifting force to the plane, the air molecule is also having downward little forces pushing from the plane, all right? So the air molecule is experiencing downward force. This caused the airplane to experiencing opposite force, which is going upwards. So this is the origin of lifting force, right? So why is Newton's third law true then? Well, this is actually very hard to explain, but I can show you by a counterproof, all right? So this counterproof basically goes like this. So there is two pens and they collide together in space, and there is no friction, and we assume an ideal scenario. All right, so if, say, when the black pen hits the red pen, the black pen casts a force in that direction to the red pen. However, let's assume that there is no force that the red pen casts on the black pen. What this means is that if the black pen travels to this direction, since the red pen does not cast a force on the black pen, this means the black pen can actually go through the red pen, all right? So it can continue to travel this way because the black pen experiences no external force, so it should travel in in this direction continuously. However, the red pen experiences the force from the black pen, so it also travels in this direction, and they are with the same velocity. This means the black pen will intersect with the red pen, which is counterintuitive because in real life, if they really hit together, they should at least go in the opposite direction, or at least the black pen should stop its motion and let the red pen go out, right? So this clearly doesn't make sense. And now let's assume that the red pen actually cast a force on the black pen. However, the force is smaller than the force that the black pen cast on the red pen. So this is a little bit confusing. You need to keep track of it, right? So what this essentially means is that if the black pen were to hit the red pen, then it will only bounce back with And this means that the red pen will travel in this direction with the velocity of the black pen. However, the black pen will also have a little velocity going in this direction because the force is smaller than the force that the black pen cast on the red pen. Alright, so this essentially means is that the black pen is traveling this direction with some velocity, and that velocity is transferred to the red pen. So the red pen is going out to this direction with the same velocity as the black pen. However, the black pen also travels this direction with an additional velocity. So the total energy, if you think about it, before and after the scenario is increased. I know this is a little bit confusing, and I know we didn't, teach about energy. However, this is the intuitive concept you need to know, right? So initially, there is only one thing traveling at one velocity, and now that thing is still traveling at that velocity. However, and magically, another thing, it starts to travel, right? So there is no energy source to prevent the black pen from traveling. So this must be not true, all right? So this is the second scenario. So let's suppose that the black pen, casts a force on the red pen, and the red pen casts a greater force than the black pen casts on the red pen. So this essentially means is that if the black pen were to hit the red pen, well, the red pen will go to this direction with the same force as before of the black pen. However, the black pen is actually going to go backward with even greater velocity, which does not make sense even more, right? So how can it, hit something and go back with a greater velocity? It clearly does not follow our intuition or the law of the conservation of energy, which we have not introduced properly, right? So this is a kind of an intuitive or simple explanation of why Newton's third law is true. And we've proved that when the black pen hits the red pen, the black pen casts a force on the red pen. The red pen cannot cast no force on the black pen, cannot cast force that is smaller than the force which the black pen casts on the red pen, and cannot cast a bigger force which the black pen casts on the red pen. Thus, it can only cast a force which is the same magnitude and opposite direction to which the black pen has casted on the red pen. This is actually confusing. However, if you really want to understand why Newton's third law is true, well, here goes to you. Alright, so this is it. Alright, so these are the two laws which we're going to introduce in this video. So in the next video, we're going to take a look at Newton's second law, which will be a little bit more complicating than the first law and the third law, right? So these two laws involves no calculation, no actual quantity calculation. It's all qualitative knowledge. And in the second law, we will introduce a very important formula, and I'll be very happy to see you then. Alright, see you. Bye.